So welcome back everyone for the second session in the morning. And Vibhor Singh from IISc is going to tell us about strong back action on the mechanical resonator using a few photons. Please.
Thank you. So I hope I'm audible as well. Okay, so let me begin thanking the organizers for this opportunity to present our work here in this interesting meeting. So I'm going to talk about a slightly different flavored physics now. Let's see how much of condensed matter physics and how much of quantum information it has. So the topic is strong back action on a mechanical resonator by a few photons. And I'll motivate it by saying something very obvious. So as I shine this laser pointer on this screen, the light reflects off the screen and reaches your eye. We are imparting a very small amount of force to the screen. The amount of that force you would say is very small. It's the radiation pressure force, which is basically imparted by the reflection of this laser light. Towards the end of this talk, what I'll try to convince you that we can see strong effect of few photons when they reflect off a mechanical oscillator. Okay. So the idea behind this Right. So this field is known as cavity optomechanics, and this is a very simple concept which you can easily grasp by considering a Fabry-Perot cavity. So consider there are two mirrors. One is fully reflective, another is partially transparent. So the distance between these two mirrors, it sets up a length scale, which sets a cavity frequency, the optical mode frequency. Assume that one of the mirror is free to vibrate. It's connected to a spring. So given this spring mass system, it will have a mechanical mode as well. Okay, so there are two resonators here, two harmonic linear modes, optical and a mechanical oscillator. So if you want to detect the position of this mirror, what you could do is shine laser through this first mirror, and when it reflects off, depending on the displacement of this mirror, it will get some phase shift. And that phase shift can be detected, and it will tell me the instantaneous position of the mechanical oscillator. So detection is one way. So, same concept is used in LIGO, for example. Using these interferometry concepts, you can get very high sensitivity. The second part of this concept is that light, it has momentum. So when it reflects off the mechanical oscillator, it applies a radiation pressure force. So if we can control the detuning of light compared to the optical mode frequency, we can also control the motional states of these mechanical oscillator. And this can be done down to the quantum limit. Okay, so there are two aspects to this story. Now, this example that I have just given you, where an optical mode is connected to a mechanical mode, the interaction between them happens via this radiation pressure coupling, where the strength of the coupling can be set in terms of shift in cavity frequency due to the 0-point motion of the mechanical oscillator. So that's the figure of merit for this system. So how good the back action or those effects are going to be are set by this single photon coupling rate defined as shift in cavity frequency due to 0-point motion of the mechanical oscillator. Now, of course, this is in optical domain, but similar experiments one can do in microwave domain by making electrical circuits, like these LC oscillators. So we can take an inductor, shunt it with a capacitor. That's an electromagnetic mode here now. The frequency is given by 1/√LC. And if we design our capacitor to be mechanically compliant, the position, the separation between these two plates will set the resonant frequency of this electrical mode. So the physics that we had there via radiation pressure coupling also exists through these LC oscillators with mechanically compliant capacitor. In reality, you make these circuits using superconducting, thin film superconducting inductors and capacitors. So this meander line that you see is an inductor, and this button-like shape that you see at the bottom is a capacitor. Okay, this is a parallel plate capacitor with top plate being suspended by hundreds of nanometer above the bottom plate. Typically, these circuits are designed in a high frequency range, something like 4 to 10 gigahertz. When you cool down such a circuit to low temperature, like 10 millikelvin, given the high frequency and low temperature, the thermal occupation pretty much goes to 0, and the LC oscillator initialized to its quantum ground state, the vacuum. The mechanical oscillators typically, as the speed of sound is much lower than the speed of light, their frequencies are lower. So typically they are designed in 100 kilohertz to 100 megahertz range. The quality factors, one can, with some engineering achieve something like close to 1 million. What it means that at these temperatures, something like 10 millikelvin, you will still have some residual thermal population of about 300 to 500 phonons. But given that large quality factor, the energy relaxation times for these mechanical oscillators could be close to 100 milliseconds or so. Okay. Now, in most of the experiments, this figure of merit that I introduced earlier, single photon coupling rate, is small. It's like something like 100 to 200 hertz. Okay, so the interaction here is nonlinear. There are three operators which are getting multiplied together. So it's like three-way mixing. But the strength of the coupling is actually very weak. So as compared to dissipation in the system, this coherent coupling is much weaker. So typically what experimentalists do, given that these two modes, mechanical oscillator and optical cavity, are far separated in frequency, they can only interact dispersively. You can add a parametric pump. You can add a pump frequency close to the cavity frequency, let's say detuned by this symbol delta here. And what it does, you can go to a rotating frame and then work out what is the effective interaction between these two modes is going to be. So if we set the pump frequency close to the red detuned pump, meaning detuning is exactly shifted by one mechanical oscillator frequency, the interaction, this three-way mixing interaction becomes more like a beam splitter. Okay, so where you can swap the excitation between mechanical oscillator and the optical cavity, and the strength of the coupling get enhanced by the factor alpha, which is the amplitude of the coherent state that you are putting in. Okay, so such type of interaction is used, for example, performing sideband cooling. Like if you want to remove phonons from the mechanical oscillator and take it to the ground state, you would use such an interaction. Another example is to set delta equals to 0, meaning drive the system exactly at the cavity frequency. That time you could see that it basically forms, if you want to perform a position measurement, this is a quantum non-demolition measurement of position of the mechanical oscillator. So to see effects like radiation pressure, short noise, etc., this is the detuning that you would use. If you shift the pump frequency on the other side towards the blue detuned pump, the interaction changes like a two-mode squeezer, where you can create or eliminate particles simultaneously in both the modes. It results into heating of the mechanical line bit and narrowing of the mechanical line bit. So these are the interactions that are possible with this simple system of two bosonic modes coupled via radiation pressure vector. Now, typically, like I said, the strength of this single photon coupling rate is very small. It's something like 100 hertz. So by putting close to 1 million photons, you can enhance this coupling by 3 orders of magnitude by a factor of 1,000. Okay, so that's a typical implementation. Where it is used in experiment, here I have taken 2 examples. Okay, so this is an example where 2 mechanical modes are coupled to a single microwave mode. And by using these red and blue detuned interaction, you can basically get quantum entanglement between these 2 mechanical modes. So again, using these beam splitter and 2-mode squeezer-like interaction, it's possible to entangle these 2 mechanical oscillators. So this is slightly different than the entanglement in qubits, because here we are really talking about continuous variable entanglement, because the variables here are continuous. Another example that I have on the screen right now is a system where you use a qubit coupled to a cavity. This is a very standard system that has been introduced in this meeting, in first lectures given by Vijay, as a photon source. So you can get a single photon out of the system, and using this red and blue interaction of optomechanics, you can get it transferred to the vibration of the mechanical oscillator. So here the circuit QED system here is being used as a single photon source, and the optomechanical system is being used to store information in the mechanical vibration of this drum resonator. So given the high coherence of these mechanical oscillator, you can have this single photon or correlation stored in the vibration for a long time. And then again, using these interactions, you can retrieve it at a later time. So this is an element which can be used to store quantum information. Okay, so given that these 2 examples, if we think about a typical cavity optomechanical system, we have here 2 bosonic modes basically, and they couple via this. And once we do the linearization, like add a parametric drive, the choices of the experiments that you can do are limited. Okay, so we started thinking or posing this question that can we get the qubit embedded between these 2? Can we get a coupling between mechanical oscillator and light mediated by a qubit or with a qubit? Okay, so this is sort of a hybrid electromechanical device, so to say. And then here the coupling with mechanical mode is implemented by this 2-level system. And given the two-level nature of these qubits, you can implement longitudinal as well as transverse type of couplings. Okay. So this is the sort of a motivation. This was the motivation for the talk. Let me get to the concept. So the concept here is that the idea that I gave earlier was that you can make these mechanically compliant capacitor, but equally well, you could also make mechanically compliant inductors. Okay, and that can be done easily by using DC SQUIDs, for example. Okay, so I think to this audience, I don't have to introduce a DC SQUID. It's basically two Josephson junction put in a loop. And when you apply external magnetic field, depending on the flux which is threading this loop, you will get some Josephson inductance for this circuit element. And that Josephson inductance is low loss, periodic, as well as nonlinear. So using this, you could make, for example, a transmon qubit. If you want to make it a displacement-dependent inductor, the easiest thing is to do, suspend one of the arm of this SQUID loop. So the vibration of this beam then would change the flux in a constant magnetic field. And since flux is changing, that will change the inductance. And if you shunt it by a capacitor, you have a shifted resonant mode. So the same radiation pressure like coupling that we had earlier can be realized by making this wire suspended. What is interesting about this aspect is though, that the optomechanical coupling, the single photon coupling that you will get, will be proportional to the magnetic field. And it's easy to understand that given the same amount of displacement, the shift in flux will be larger if we are calculating it at a higher magnetic field. So the shift in frequency will be larger, therefore larger G naught. So you get a system where the single photon coupling can be tuned by increasing the magnetic field. Okay. So this is the sort of a concept behind the device. What we do is essentially, this is the SQUID loop, not completely visible in this same image. These are the two Josephson junctions here. And it's basically forming a complete loop. And this thin yellow line that you see here, that's a aluminum nano beam. It has a dimensions of 50 micron long, 200 nanometer wide, and only 28 nanometer thick. It's more like a nanoscopic version of a guitar string. Okay? Given the length is small, the frequencies will be higher. What we do is then take the SQUID loop, shunt it with two capacitors, make a transmon qubit, and put it in a coaxial cavity resonator. That's the microwave mode. That's a standard CQED setup where a qubit couples to a readout resonator. Yes. Yeah. It's freestanding. It's free to vibrate. So so this little gray and bluish region that you see, that's the region where we selectively etch and remove the substrate under the wire. All right, so so this entire thing then goes in a parallel magnetic field. So if you can see that if we apply parallel magnetic field in the plane of the SQUID, any vibration which is out of the plane would change the magnetic flux. And by applying a parallel field, we can detect the vibrations which are out of plane. We also can do experiments in perpendicular magnetic field, then we become sensitive to the in-plane mode of vibration. All right. So just to remind you, the device that we are dealing is basically a flux tunable qubit where we have designed the frequency close to 8 gigahertz. We have embedded a mechanical mode, which has a resonant frequency close to 4 megahertz. And the coupling between these two is longitudinal, meaning any displacement of the mechanical oscillator change the splitting of the, between the first two energy levels. And just as a standard circuit QED platform, we have a dipolar coupling between the cavity mode and the flux qubit. So the system is very similar to like a trapped ion system where you have an internal degree of freedom, which is like the spin or qubit in our case. And it has also got a micromotion, which in our case is the mechanical mode. So this is very similar to like a solid state implementation of a trapped ion. Now, what can we do with it? So we perform microwave measurements. The simplest is to do the cavity spectroscopy. So what you do is check the transmission through the microwave cavity as a function of frequency and while changing the magnetic flux. So what will happen here, the blue curve shows really low values of transmissions, and the red curve part of this 2D plot shows the high transmission. So if you imagine like a vertical slice on this cut, you will see sort of a Lorentzian curve. Okay, so at around 6 gigahertz, we have high transmission. That's the bare cavity mode. And as we tune the frequency of the transmon qubit, by changing the magnetic flux through the SQUID loop, the transmon qubit and the cavity become resonant, showing the standard formation of new eigenstates, showing the strong coupling between the two. And the transmon frequency is minimum at 0.5 flux quanta. So we again recover the bare cavity mode. And then, this is a periodic function, the inductance of the SQUID loop. So this process continues. So we can do this in the first lobe of this avoided crossing, but you can continue this experiment, apply more and more magnetic field, and then see this avoided crossing will repeat. And we would like to do this because we want to see electromechanical coupling, which is larger when we have large magnetic field present. Okay, so how do we measure the mechanical mode? So to measure mechanical mode, we borrow the technique again from cold atom community, which is to do an experiment similar to electromagnetically induced transparency. What you do, you continue to measure your rest mode when the qubit and the cavity are nearly resonant. And you add a sort of a pump tone, which is detuned by one mechanical frequency at the first mechanical sideband. What happens that the radiation pressure force that mechanical oscillator is going to encounter will beat close to the difference of these two. And if this difference of these two frequencies equal the mechanical oscillator, it will undergo a coherent motion. That coherent motion will scatter these pump photons and interfere with the probe, producing an interference window if we zoom in really at the top of this peak. So what I'm showing you here is the transmission of the rest mode, which is around 5.88. And right at the top, in presence of a pump, what you see, there is a very tiny absorption window, close to like 10 dB. I would really like to point out this, that pay attention to the axis here. This is several megahertz on the x-axis. What we are looking at is 200 hertz only. So this entire curve is sitting right at like 1 pixel on this curve. Okay, so this is the absorption window that opens. By measuring this absorption window, we can tell our mechanical frequency, which is about 4 megahertz or so. This experiment is quite useful because in a sense that it helps in determining the mechanical resonator properties, also to characterize the strength of electromechanical coupling, single photon coupling rate. So such experiment can be done at different pump powers, and we can see that the line width of this absorption feature scale linearly as we increase the pump strength. And from the slope of this, and by carrying out stark shift experiments on transmon qubit, we can calibrate what the single photon coupling rate is. So for this particular experiment, we have measured something like 35 kilohertz single photon coupling rate at 25 millitesla applied field. This is sort of a nearly 3 orders of magnitude improvement over the conventional devices. Okay, so of course, electromagnetically induced absorption is one way to characterize mechanical oscillator. We could have done much simpler experiment, which is we just send the pump tone at delta equals to 0, resonant with the rest mode, and look at the phase noise of the microwave which is coming out. That's much simpler. So we do those experiments as well. So this is the measurement of power spectral density around the mechanical sideband that will come if we send a pump which is detuned at 0 frequency. What it does, because detuning is 0, there is effectively no back action on the mechanical oscillator. So this gives us information about its bare characteristics. So we measure a line width, which is close to 6 hertz. That's the line width of the mechanical oscillator. And frequency matches same as the one in EIT measurement, close to 4 megahertz. Another important parameter that comes out from such measurement is the thermal occupation of the mechanical mode. The area under this curve is related to the how much thermal energy it has, how much thermal energy the mechanical mode has. So by performing calibration of our microwave tones, we estimated that the thermal occupation, phonon thermal occupation for mechanical resonator is close to 360 at the base temperature of the dilution fridge. Okay, so next what we can do is start asking the question like what will happen to these line width and shift in the mechanical resonator frequency as we make the pump detuning non-zero. So as we change the pump detuning, remember that there are 3 types of interaction that I introduced earlier. When pump is detuned to red side, the red sideband, blue sideband, and delta equals to 0. So at delta equals to 0, there is no back action. So you recover the features which will be same as the bare resonator frequencies. But as we make the pump detuning more negative, we are going towards the red sideband. We see that damping goes up. And these 3 panels are 3 different pump powers as a function of pump detuning. So as we increase either the pump power or the detuning towards the red, we see that the line width is actually increasing. So here we started with a mechanical oscillator, which is 6 hertz in its line width and achieved close to 100 hertz while doing the back action sort of a measurement. I don't think I have the time to explain you what the dotted and the solid curves here are, but we try to do some theoretical calculation by treating this rest mode as a Kerr oscillator and compute how much back action would be there on mechanical oscillator. And the upshot of the calculation is that a simple Kerr-like model does not really explain the back action on the mechanical oscillator. One has to go beyond. So if we do some corrections to the theory and treat it numerically, like using qubit as a weakly nonlinear oscillator, we get these solid black lines, which matches with the experimental data a little bit better. Okay. Now, yeah, so these are powers which are actually quite low. They're still like, if you turn these powers into number of photons, these are fractional photons, like less than 1 photon. We can continue this measurement at higher power as well. For example, if we measure the rest mode at a high power, so this is a measurement at low power, minus 24 dBm. This is sort of a linear response of the Rabi mode. But if we increase the power, the higher energy levels of the transmon qubit, they start to modify the response. So at high power, the occupation of these higher energy levels is non-zero, and this basically changes the response of the rest mode. And it becomes quite non-trivial. And if we continue to make power more and more, the transmon qubit get fully ionized, so to say, and what you see is the bare cavity response. That's this orange curve over here. So we still ask the question that, let this response of the Rabi mode be changed, but are we still getting cooling? Do we still see backaction effect? So if we perform the measurement like I showed you earlier at minus 4 dBm power, where clearly the higher levels are playing an important role, we still see that the line width broadening continues to grow, and we see close to like 550 hertz line width at a power of minus 4 dBm and a detuning of something like 10 megahertz. If we convert these numbers into the performance of the cooling, so we started with a mechanical oscillator of 6 hertz line width, which will correspond to close to 360 thermal phonons. And given this line width, the mean thermal occupation of mechanical oscillator would correspond to something like 8 phonons. So we perform a sideband cooling, and this is all done with less than 1 microwave photon. So using just less than 1 microwave photon, we are able to take the system from 360 phonons to 8 phonons. So I'll stop here. So just with the summary and prospects of the talk. So the maximum single photon coupling rate that we have been able to achieve in this device is close to 60 kilohertz. And what it does, using less than photon, we can cool down the mechanical oscillator down to 8 phonons. Why 8? It's basically getting limited by the sideband resolution parameter. The rest mode line width is something like 12 megahertz. The mechanical oscillator frequency is 4 megahertz. So the sidebands come within the envelope of the rest. If we can make the device sideband resolve, those mechanical sidebands will be outside, and this ultimate cooling occupation that we have would be less than 1. So by controlling the line width of the rest mode, we see there are prospects in cooling down the mechanical oscillator to its ground state using less than 1 photon. So that's the kind of engineering in light matter interaction that you could do, where effects by few photons are so strong. Okay, so this is a work done by graduate student Tanmay Bira, who is writing his thesis now. We have done a series of papers on this topic. So if you're interested, feel free to go through these. So with that, I would stop, and thank you for your attention.
Questions?
So you had 8 phonons. You had 8 phonons when you were still coupled to the optical cavity, microwave cavity. Can you now somehow adiabatically take away the cavity and leave the mechanical oscillator behind with just 8 phonons? And how long would it last?
Yeah. It's totally doable in the scheme of things that we have here. We haven't done the experiment, but the expectation is, given the line width is 6 hertz, it should stay. Exponentially, of course, it will change, but then it will take close to like hundreds of milliseconds before reaching the thermal occupation of 360 again. So that time would be hundreds of milliseconds, given the 6 hertz light width.
But the time for one thermal phonon is microseconds, maybe.
Tens of microseconds.
Tens of microseconds. My question was, could you use, or have you tried to use a higher frequency mechanical mode so that just, you would have fewer thermal phonons just by
so,
Weizmann?
Right. We have thought about it. It's ultimately like an optimization. So the next set of devices that we are planning are with shorter wires, so that frequency is higher. The frequency that we got in this device was based on the fabrication outcome, like how much residual stress you have in the aluminum that decides the frequency. But yeah, if we make a shorter wire, we can have the frequency.
Or the same wire, but higher modes. There are not higher frequency mechanical modes?
So, okay, no, okay, understood. Yeah, so one can use the higher modes, higher harmonics of the same mechanical oscillator. But if you do the math for the coupling, given the symmetry of the mode, you can get cancellations.
More questions? If not, let's thank Vibhor again for the.